Alright, I guess we'll get started now. So even though today, like, it looks like there are fewer people than last time. So I don't know, but how many of you were here last time, like last week here? Alright. Okay, so yeah, we're basically talking about the DP last class, which is dynamic programming. And this week actually we'll be covering like DP as well. So but it's gonna be like a little bit harder. And yeah. Okay, wait, Jane, you're here like on Monday, right?
Hmm?
Sorry, you were like in Monday session, right?
Yeah.
As well. Okay, never mind. Okay, it's fine. Alright, so I guess we'll get started now. So this week we'll be talking about dynamic programming again. But this week we'll be focusing on like basically like a little bit harder problems. Like what kind of like harder problems dynamic programming can use to solve those. And so before doing that, we want to like basically do a little bit of review of what dynamic programming is. So how many of you like have never heard about dynamic programming before? Like never heard about? Okay, sure. Okay, dynamic programming basically just it's pretty like it's really complicated. Like I mean, I'm not trying to like freak you out here, but just the idea is that like even if you are really good at competitive programming, dynamic programming can still take you a while to understand like what's going on, like in a lot of contexts. And even if that's the case, it still takes you like some time to learn a lot of to see a lot of problems and to try to start from there. Yeah, but with that being said, we're just gonna cover a little bit like a review of what dynamic programming was last class. So we covered this idea that dynamic programming is just like a combination of two really like contradiction ideas. One's brute force, and the other one's like the care for. These two words. So basically, the idea is that you want to do the brute force, but instead of using like just the brute force, you want to do it in a careful way. Or specifically, you don't want to like repeat any computation you do. So you introduce this idea called member table. So which is basically just a hash map or like an array, which was could be one-dimensional or multiple dimensionals. And once you introduce this idea, okay, let me just say, okay, so once you introduce this idea, basically you can treat the recursive call. Oh, by the way, all of the notes are on the GitHub, so like you don't have to write it down or anything. So basically, if you have once you have the memo table, you can treat each of the recursive call as all of one, which is basically constant time, right? And this is basically, I think, one of the greatest benefits of using dynamic programming. That once you have something already computed, basically just retrieve it from the memo table. As opposed to if you merely have a brute force like algorithm, you have to do it like every time you compute it. So that would be like an exponential time. So last time we covered basically 3 different problems. One is that we covered the nth Fibonacci number, right? This is the first problem we covered last time. And the second one is the Bellman-Force algorithm, or the shortest path algorithm. And oh yeah, we basically covered those 2 problems, not 3. So I want to spend a little time like at the beginning today to cover like so we want to say like what would be the 5 steps to explain or like at least to I mean at least to explain, sometimes even to help you think about like what dynamic programming like is event like is designed. So yeah, I'm gonna write. Okay, so there are gonna be 5 different steps when you think about dynamic programming. So the first step is that you want to define a subproblem. And the second step is that you want to guess partial solution. And the third step is that you want to relate the subproblems. And fourth step is that you want to use recursive or recursive memorization plus memorization. Or build a bottom-up approach. Yeah, it's just on my notes, so And last step is just to solve the original problem. Okay, so these are the briefly 5 steps of not necessarily to think about it, like not necessarily how to design that programming, but definitely help you to explain it or to think of it in some way. Yeah, because a lot of times like it's really creative to think about like how dynamic programming can be for. Yeah, but I'm gonna briefly walk you through like what we covered last time about like more specifically. I'm gonna go through each of the steps and apply them to the like problems we encountered last time. So the first problem we covered last time is called Fibonacci number, and the second one is the shortest path. Okay, so if you see the first step for the Fibonacci number, what is the subproblem in this case? It's just if fk, where k is from 1 to, right? Because we're trying to compute the nth Fibonacci number. In order to do that, we have to compute all of the previous -1 terms in order to find the nth Fibonacci number. And that would be the subproblem, like which is the first step. And for the shortest path, we used this notation that beta k from S to V, where V is just for all nodes, and k is greater than or equal to 0, less than like magnitude of the V, right? And basically this notation is saying that you want to find the shortest path from the source node to the target node or the B node. So you can imagine that you have a single source and you have a V, which is another node. You try to find a path like that leads you to from the source to the destination node, gives you the shortest way among all of the possible paths. So that's an optimization problem. So we want to use the notation that beta k, which from S to B. So this is what we say the manual table in this case. But this notation itself means that if you want to use like no more than k edges in order to traverse from S to B, where S is the source node and B is the target node. So yeah, once we define our subproblems, we can compute like how many subproblems are there, right? In this case, if we have the Fibonacci number, there will be like number of subproblems will be n, right? Because there's just from 1 to n. And in the shortest path problem, like number of the subproblems a little bit like harder to think about it. But eventually, like V could be any of the node, right? So V is a variable, S is a single constant, which is like the single source node, and V could be any of the like other nodes. So the number of V could be like V itself, and the number of K could from 0 to the magnitude of V, which is this V itself again. So the number of subproblems we have in this case, we just do n squared. Okay. So this is the first step. We define the subproblems and the number of subproblems we obtain after we define. And the second step is that you want to find out what is the gas, right? So in the second step, like, okay, so I said this thing is called gas because, okay, so what you literally do in dynamic programming is that you want to take a possible, like you want to try to find a solution, like you want to find a solution, you want to try to guess part of the solution. So there could be like, so at least in this part, right, what do you, like in the shortest path scenario, what you're trying to guess is that you want to try to guess like which is the last edge you are entering before you enter the destination node. In this case, there could be like 2 edges, right? So this would be the guess. Right? These 2 would be 2 of the different options before you enter the destination node. So this is what I mean by like you have to guess part of the solution. So yeah, but a lot of time you're gonna find that like. So for a lot of dynamic programming problems, you're gonna find that there are a variety of ways to guess. So it's not just gonna be like one single way. You can also guess in this case like which would be this like last node you traversed instead of the last edges. That's also valid. But like depending on the type of guessing you're making, it could make your problem like more computational hard or easier. So yeah, that's also the artistic part like about dynamic programming. But like for the Fibonacci number, it doesn't involve any guess, so it's just like gonna be one constant, right? Because it literally all you have to do is just to find the fk is just fk minus 1 plus fk minus 2. So all the previous 2 nodes, all the previous 2 values you added in together. It doesn't involve any guessing. So but for the shortest paths, right, you want to guess all of the possible edges leading into this target node. So there could be, in the worst case scenario, I mean, in every scenario, there could be n degree of the cases, right? Because all of the edges could be a potential guess, like could be a potential solution to the optimization problem. So you want to include all of them. So in this case, the number of guesses you have is the n degree of v. Okay. And the third step is that you want to find the mathematical formula in order to relate all of the subproblems. So that, okay, in this case, it's actually quite simple because the mathematical problem just gonna be the Fibonacci formula here, where fk is the case term is just the fk minus 1 plus fk minus 2, right? And in the other case, you want to find the match formula. But this one is for the shortest path, it's going to be a little bit complicated. But eventually, what you're doing is that you want to find the beta k from S to B. So this value is just equal to the mean of all of the possible. Okay, let's see. Oh yeah, beta k minus 1. Yeah, so what is this thing is that basically you want to find the shortest path from S to B. So you want to break down this problem and relate to the previous problem you have already solved, which is that you want to find the shortest path from S to U, where U is another node. But you gotta guarantee that U leads to V, right? Because so eventually what you're guessing is that the way you relate the problem is that you try to find the edge to any of these two nodes, in which case this will be U. So after you find the shortest path to any of these nodes, you know that this node will lead to the eventual the destination node. Then the shortest path is just gonna be the mean among all of the possible scenarios. Does this part make sense? This was from the last class, so yeah. But okay, but the last step of this part is just gonna be all of the n degree V. This part is just going to be all of one because it's just math here. Okay, so number 4 is we want to do a memo table or build up a. So we want to do either. So there are two ways to do dynamic programming, two ways to implement it. One is use recursion and with a memo table. That way, it's different from brute force. I mean, if you do it only with the recursion, we mentioned last class that it's just going to be brute force and it's going to be exponential. But once you introduce the memo table, it's going to be way faster polynomial. And the other way is that you can use you build up bottom up approach, which basically is a bunch of for loops. So I mean these two theoretically they have the same complexity and should take the same amount of time, but in reality when you do the DP, a lot of time you want to use this approach as much as possible, which is you want to use for loops and try to build it from bottom to up. I guess I will release some problems today. It could be more interesting and more practical. If you look at a specific problem and try to think about what's really happening. But okay, the idea is that whenever you do dynamic programming, there are two approaches to do it. You want to use the for loop instead of the recursion because for loop saves you a lot of the function calls. So each time you do the recursion, it's gonna give you 2 function calls. So and you're gonna see that in the memory stack, the function call is gonna build up. So it costs a lot of memories, and sometimes it even costs which sometimes we can call stack overflow, which is just you have too many function frames, which is thousands or hundreds of thousands. So, but if you have the for loop, that's not a problem because you don't have involved any. You just have one function call, and that's it. So, but this approach, build from bottom up, a lot of times it's harder to think about. But even although theoretically that exactly the same, but I think personally I feel this way if you use recursion is way easier to think about. But when you code it out, you want to use the bottom up approach. Okay, so and the last part is that we want to solve the original problem. So we didn't mention this last time because we didn't mention it last time because so basically what this saying is that you want to solve the original problem after you're done building the DB table or you're done solving the recursion. So basically, for this part, the last part is saying that you want to find the value of the fn, right? So basically, you have computed all of the fk, where k is from f to 1 to fn. So you want to retrieve the fn's value from the table, and return its value, right? And sometimes this takes extra complexity because in this case, you're using a hash table or array, which takes you only constant time. But sometimes it's going to take you more time because, so for example, in this case, right, if you want to find solve the original problem, which is you want to find the shortest path from the source node to the target node, you want to exhaustively find all of the possible, so you want to go over the whole loop. Okay, yeah. So you want to go over the whole table again. So in this case, okay, so you want to solve the original problem. The original problem asks you to solve is that like single source all of the target nodes. So you want to go over the whole table again with this part being v magnitude -1, which is basically saying that you can use no more than v -1 edges, which is the most amount of edges you can possibly use. And then for all of the v, so basically this is a loop, right? And this helps you solve the last problem, which gave you a complexity of O of v instead of O of 1, right? Because this case, you have to do a loop again. But okay, what is the thing is that sometimes you have to do extra, you have to introduce extra complexity to solve the last part. But the complexity normally is very low compared to the process when you build the DP table. Does this make sense? So far, or a little bit? I know DP is really confusing. Personally, it's confused me a really long time. So, but I mean, well, I covered 2 problems today, so hopefully it's gonna get a little bit better or worse. Another thing is that once you get good at at least a little bit better at DP, you're gonna find that a lot of coding questions become relatively simple. For example, if you have experience with Google Keystart or Facebook interviews, you're gonna find that a lot of problems, at least one of them, especially in the competitive environment, at least one of them is gonna be with DP. And normally that's gonna be either the hardest problem or the second hard problem. Yeah, at least that's my observation a long time. The really challenging problems with those interviews or the coding competition is gonna be really with DP. So that's how amazing this thing can turn out to be. But also it indicates that it's really hard concept to math. Yeah. Okay, so the first problem I'm gonna see today is called past justification. Okay, so both of the 2 problems. So one is called test justification. This is the first problem I'm going to cover. And the second one is called blackjack. So just as a poker game. So both of these problems are extremely practical. So by the time you probably done these 2 problems, you're going to find that DP can be turned to be really useful in the industry scenarios even. Okay. But okay, so they gave you a little background of what this thing can be used for. So text justification, okay. So say you have a Word document, right, or it's a page if you're on Mac. So let's say you have a Word document. So what text justification allows you to do is that you have a bunch of text. It's just basically typing on the Word document. So what this thing allows you to do is that basically it aligns your text in a very nice way, such that, okay, so let's say these are all of the texts you wrote on the document. So there's an optimal way, technically speaking, there should be an optimal way that such that if you align it in such a way, it looks nicer. And that's what basically text justification is saying. So for example, okay, so when you are writing on the Word document, right? So for example, the first line, the width of the first line is fixed, right? So you can put a lot of words on this, but the document itself, the software of document, it's gonna make a choice that whether it's gonna shift you shift you to the next line, or it's gonna stick to the same line. So whenever you're typing, it's gonna make that choice. So that choice is using like the DP algorithm, which is text justification, to solve that part. So basically, it's making a choice based on like how nice your document will look like. So whether it's like should it slide it to the next line or should it stick to the same line. So yeah, that's the thing that we got like covered for this part. Okay. Yeah, does this make sense? Or like what it means like for it to be like text justification? Okay. Yeah, gonna see like why this thing related to DP now. Alright, so yeah, I hope it's not too like suffering like the DP. Yeah, even though I know it's really hard. Okay, so basically for this problem, you're gonna have two different inputs. The first input is you're gonna have a text, which is just a list of words, right? So you have a long list of words. You can imagine this as being all of the words you typed previously. And you want to put all of these words into the document. And the second input you have is called badness, which is basically a map. So it takes two arguments actually. So what this second argument gives you is that badness basically saying that if you let's say you have all of these words, right? So text is just a list of words. So for example, I like programming. Okay, so all of these are words. So you can imagine this as being the content within all the words here. So you can imagine the first one, text, is just a long list of words. And what badness gives you is that, let's say if you have a badness, it basically takes two parameters. And the first one is the index of the first word. And the second one is the index of the last word. So let's say if we give it 0 or 3. Right? So if it is 0, 3, basically means that, so if you index this, so this is the first word, second word, third word. Or I like. Okay, this is the first word, this is the second word. So this is the second word, this is the third word. Okay, so 0, 3 basically gives you, sorry, this is 2. So there's 0, no, actually, 0, 2. So 0, 2 basically gives you the, so this is saying that if you take these three words, I like programming, because it's 0, 2, right? From the first word should start from 0, and the last word should end at 2. So badness basically is saying that if you use these three words, I like programming, and you put them on one line, how bad this line is gonna be. So it's basically like a penalty function, in a way that if this thing is really high, it means that your text looks really bad. So the words, like basically the objective we have is that we want to put all of this long list of words into a Word document, such that the penalty we have is as little as possible, or the text looks as nice as possible. So I mean, theoretically, I don't have to go over this part, but if you wonder how this thing is implemented, it could be like a simple math function, right? For example, it could be like infinity if the text doesn't fit the line. So this, basically this is saying that the penalty is going to be really high if you have a long list and you're trying to put all of the textures into one line when actually this line doesn't fit. So it could be the case that you have a really long, you want to put all of the words on one line, so that's not possible. So in that case, it's going to give you the penalty that's infinity, which is saying that the text doesn't fit on this line. And alternatively, if the text does fit on this line, the penalty function is going to be the page width minus the text width and to the third. Right. So this is saying that if the text does fit on the single line, which is saying that if the I like programming, if it does fit on one single line, right, I can write it here on one single line. In that case, okay, so the penalty function is gonna, like the way we compute it is that it's gonna give, like, first it's gonna take the page width, which is this part, right? So you have a, like a Word document, in this case, like, page width should be your, like, the width of your computer, right? And that should be the page width, which is constant all the time. But the text width is gonna vary because based on what words you put into the single line. Like the text width is gonna vary. In this case, you have 3 different words. So if you count the character, right, this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. About 13 like words, about 13 different characters here. So text width in this case is gonna be 13. So the difference between these two, if they are too high, right? So it's gonna give you a lot of penalty, which is to the third. So this is the way that like how the thing like measures how bad your line is. So this is basically your penalty function, and your objective is to minimize this globally. Does this make sense, or sort of make sense? Like, okay. So yeah, hope we're not into DP yet, so don't panic. Like it's still like easy part. Okay. So the problem we have right now is that we have this long list of words. We try to put it onto different lines, like on the whole document, right? So we're gonna determine that how to split this like document, how to split this long list into different lines in order to make the global badness function, like the penalty function, as low as possible. Okay, so can anyone tell me why greedy algorithm, if you heard about like greedy algorithm before, why it won't work here? Or do you think it should work, like will work? Like the greedy approach. I mean, I know like we didn't cover greedy approach in this like club, but if you ever heard like why do you think why it wouldn't work here? Any idea? Sonny? Oh. Yes, you have an idea. Why greedy approach won't work?
I don't know. Sorry.
Oh, it's fine. Okay. Yeah, basically, okay. So the greedy approach, the reason it won't work here is because okay. So we're trying to do the global optimization, right? It's not a local optimization. So greedy approach, the greedy approach basically is saying that you want to make all of the choices whenever it's locally optimal. So for example, in this context, right, if we have like every line, so every line you have to make a choice that whether to split or not. So the greedy approach, if you have the greedy approach, you would try to fill the first line as much as possible. Does that make sense? As long as it doesn't overflow. That's the greedy approach, because the greedy approach, what the greedy approach really is doing is that it's trying to minimize this function, right? So they have so as long as I can put a word here, I want to always put a word. That's what the greedy approach would do, right? But the reason it won't work is because we're trying to achieve the global optimization instead of local minimization. Local optimization. So if you fill the first line too much, you can imagine a scenario that, like for example, we have four different words, right? I like programming because. So just to say that we have 4 words, why this case won't work? Because if you fill the first line, let's say if you fill the first line, if you fill the first 3 words into one line, and on the next line you're just gonna have the programming, right, alone. So it's gonna give you a huge penalty on the second line, in this case. But in this case you're using greedy algorithm and try to fill the first line, which you did. You feel like you put all the 3 words on the first line. And then the result is that the fourth word is gonna has to fall on the second line. And it's gonna give you a huge penalty because the fourth word is on the next line alone. Right? So in this case the dynamic programming approach would instead do something like this. So it would still it would put the first 2 words instead of the first 3 words on the first line. And move the third word, which is programming, on the second line, along with the because. That way, the second line has 2 words instead of 1. I mean, okay, this way, you can imagine that this way, the first line is gonna give you a little bit higher penalty, right? Because you only have 2 words instead. But the second line is gonna give you less penalty because you have 2 words. It's more like a balance scenario, you have a trade-off. But in greedy algorithm, it doesn't know anything about trade-off. It's always trying to optimize the situation at front. So that's why we can't really use a greedy algorithm to solve this one. Does it make sense? or at least I think the Microsoft Word software was trying to use the greedy approach. At least before the latest version, it was trying to use the greedy approach to solve this problem, which is sometimes looks really ugly. But I think the updated one is using dynamic programming. Yeah. Okay, so we're going to the programming part now. So far does it make sense for you don't have to understand how these two functions are implemented. You just have to know basically this bandness function takes two indexes, which is the indexes. All of these two indexes are the index of this list, and it's saying that if I split this, for example, give you 10 and 20. If you have two indexes 10, 20, is it saying that I want to split the word from 10th word to the 20th word and put them on one line, and how bad that line is gonna be. So this is like a black box function. Can you imagine that? Yeah, and text is just gonna be like a long list. How will we use dynamic programming to determine where to cut this text list into different segments and put them on different lines and minimize the bandwidth function. Any idea? Yeah, using dynamic programming. Yeah. Any brute force idea? Any idea to use maybe you can use brute force to solve this problem? How will you do it? Any idea? Okay. Jane, do you have any idea?
You decide which word the next line is, which word starts the next line.
Exactly. Yeah, that's true. Yeah, that's right. I was about to ask what the brute force would be like, but you already said dynamic programming the approach already. But yeah, I guess I'll repeat what you said first. So okay, so here you want to solve the dynamic programming in the dynamic programming way. Okay, so review let's recall that how do we solve dynamic programming. So these two different steps, these two steps are the most important part of solving dynamic programming. So once you once you do the first two steps, everything else becomes a little bit mechanical. So once you have the subproblems and the guess of part of the solution, you have these two parts down. You can write down the math formula on the third part very easily. So in this case, what we're trying to see is that how to guess the solution. So what is the solution we're trying to guess? So yeah, Jane already said that basically what you do here is that you ask the question, where will the next line begin? Okay, so let's see how that will work here. Yeah, okay, I'm gonna read this part. Okay, let's see how that will work this part. Okay, so we have this long list of words, and you ask the question how the next line will begin. That's basically the second part, right? That's the saying that guess part of solution. So you're making a guess that where the next line will begin. So we know that for a fact that the first word, right, definitely gonna begin the first line, right? So that's beyond doubt, right? So the first word I will occupy the first line necessarily. So yeah, so this part is like a base solution, base case, right? Because the base case is just gonna be the first word. It's gonna start the first line. And so the next question is what will start on the second line, right? And then after you figure out that part, you basically ask what will start on the fourth line, and so on, until you run out of all the tasks, right? That's basically the guessing I'm making here. So what would be the so let me think. Okay, so what would be the subproblem in this case? Do you know what do you think is the subproblem?
Basically, for each line, you measure the badness of each possible line, and then that would be the subproblem.
Let me think about that. Oh, you mean basically okay, so you measure the badness of one line, and then you go on to the next line, and you do on recursively.
Yeah, each line is the subproblem.
I see, okay. Yeah, so basically, okay, you can say it actually in one word, so technically it's called suffix. Yes, a comp sign term, which is called suffix. So what suffix basically means is that, so if you have a word, right? Normally, if you learn, like, say, linguistics, linguistics, if you have a word which is, let's say, perfect, right? The suffix is just going to be the end part of this word, right? So I don't know if this is a word or not, but okay, let's say the FECT is just basically the suffix of this word, and prefix is just going to be the previous part, like all of the part that's like starting with the beginning. That's the prefix, and suffix just the all of the parts that's ending with the end. So this is the prefix and this is suffix. So what basically solving the problem is that we're going to try to see what is it basically the subproblem is just the suffix. So in the way that so each time you make a decision, you always have something left. So that something left is gonna become your subproblems. You're gonna try to solve, and each time you solve it, and each time you have what you have left is the suffix. Does that make sense? Or so imagine that this long list, right? This is a long list. So try to imagine that why suffix would work, how the suffix means here. What does it mean? Basically, you're trying to cut this long list. So first cut is definitely gonna start from here. This is the first word, and the second cut is gonna cut somewhere here, right? And then you suddenly have a sub list of it. Does it make sense? The first line is gonna be this. You cut it here. This part is gonna be the first line. And suddenly you have a long sub list instead of the original list. You have a shorter list, and that shorter list is gonna be your subproblem, which we call suffix because it ends with at the end. So that's what it means. I try to use the single word to explain what the suffix means. But here, suffix just means that starting from the beginning, you make a cut, and then you put this on the first line. You have a sub list left, and you try to solve how that sub list will be distributed on different lines. And that sub list is called suffix. So the subproblem we just say is a suffix. Okay, so more specifically, the subproblem is gonna be using a Python notation. It's gonna be word I colon. This is a colon, right? Word I colon this. So this is saying that all of the words are starting with I index, where I is just another subproblem. Original I is just the zeroth one because it's all of the whole list, and then you can make a cut and I becomes that cut. Then you try to solve that problem. That's a subproblem. Okay, so the complexity of this basically how many guesses are there, how many possibilities are there in order for it to start on a new line. How many are there? Should be just n, right? Where n is just the number of words. Because you're asking the question that which word will start on the next line. So the worst case scenario just gonna be you have to try all of the words. So all of the words have the chance to start on the next line. So that's just gonna be n, right? So where n is the number of words you have. And that's the the first the subproblem part. And guess is just gonna like what Jane said before that we want to guess at where to start the second line, right? So where to make the cut. So number of choices we have, the number of choices we have for guess is just gonna be a minus one, right? Because you already have determined that this first word will end on the first line. So you want to make a guess that of all of the next n minus one words, where would which one of them will start on the next line. So number of guesses you have is n minus one. So complexity, the complexity would just be the number of subproblems you have with number of guesses, which is I mentioned that's actually not true, but in this case coincidentally the complexity of the algorithm is just going to be n squared. Basically just the number of subproblems you have with each of the guesses you have to take for the subproblems. You times them together, you get n squared. That's the complexity of this algorithm. Okay, I know I'm a little bit this is really confusing, okay? Or at least a little bit. Yeah, okay. You'll get used to it, especially if you've done some problems. Okay, so, yeah, basically, so the DP table we're doing here is just gonna be DPI. We're just gonna write it down, not to asking, you have to understand what it means, but yeah, some part of it I don't even understand, completely what it means. Okay, so DPI is saying that like DP table like as index, which is like equal to the minimum of the badness. Plus DPJ, where J is from I1 plus 1 to N to N. Okay, so what this means? So this is like the third part we have. So how do we relate the subproblem? Right? So this is saying that, okay, so for each of the DP problems, so we're trying to optimize the cost, right? So the way you do that is you basically try, like, you have to see from right to left word. Like let's see from the right word first. So what it's saying is that you basically try out all of the possible J, where J is just where the word ends. I is where the word starts, and J is where the word ends, right? Because we say lexical is IJ. I is the start, J is the end. So you're saying that, okay, so the cost of the line, of this line, starting with the S word, it's gonna be the minimum of all of the possible choices here. And more specifically, all the possible choices you have is basically you have a J, where J is the place where the sentence ends. So you want to try this J from I plus 1 to N. Because I is the starting word. You don't want to include the starting word. You want to find the end word. So all the end word could be anywhere, like starting from the starting word. Any of these both words. So it's like it should be J is starting with I plus 1 to N, or N the last word. So it could be like the second word right next to the starting word. That's your place. That's the place you end. Or it could be the last word. So you want to try out all of these possible different choices. So eventually, this is the guessing part, right? This is trying to find out. This is trying to go over all of the possible guesses, and then you select the minimum of them. Right? This is the minimum part. So DPJ is just saying that. Okay, so if you end the sentence, okay, DPJ. What is DPJ? Yeah, DPJ is saying that. Okay, DPJ is saying that. So this sentence is equal to like this I, right? This is the I. I is the place where you start the sentence, the current sentence. J is the place where you end the sentence. So DPI is equal to DP, the badness of IJ plus DPJ. So this is because you have an IJ as one sentence, right? And then you already have like what would be the cost of this sentence, which is minus IJ. And then you plus J because J is gonna be the subproblem you compute. J is basically saying that starting with J's index, what will be the cost there? Like after this suffix, what will be the whole cost of the suffix? That's the J. And the I is just the like the current starting place. J is the subproblem. Sort of makes sense, or okay. But this is like this part is the most important part of the DP. So if I give you this part, you should be able to understand immediately how to solve this DP problem. Like all this thing is this math formula here. Yeah. So so J is just all the possible positions where the next line can, like where the line after I can start. So I is the current position of where the line can start. J is the position of where the next line, where after I is S line can start. So IJ is just this current line, but J is going to be the next line, like all those subproblems. I hope it sort of makes sense. Yeah. Okay, so the base case is just going to be as we said before, like the base case is just going to be the first line. It's going to definitely start from here. Okay, I guess this is sort of makes sense. Yeah, so after you've done all of this part, you go to the fifth part, which is solve the original problem. Which is, in this case, just going to be 0, right? Because you try to ask that what will be the like the global cost here, which is just stored as the 0th element of DP. So yeah, I mean technically you can use like two different variables here. Like you can build a two-dimensional DP table. Like instead of with I, you can ask what is the starting and end position, right? That's also sort of makes sense, but in this case we won't have to use that because we know that like the sentence is gonna be consecutive, like it's gonna be continuous or consecutive. So you always know that like you have to end here. That's like you always know that as long as you end it here, you always have to start with the next word. So it's also going to be like built consecutively. So that's why we say one variable, we just have to use I instead of ij. So I mean, a bad DP in this case would be that like you have a DP table and the index is going to be ij, right? And that would be kind of bad because sort of you have to like deal like you have to think over like how that would like go up. But it's definitely going to be harder than this one. But that's actually what the most people would think about, like where the line will start, right? That sounds like where you have to define the start and end position. Where in reality, actually, you just have to find out where the end position will be, because the line always starts at the beginning. So that's why like this DP is better. So that's also why like DP can be like quite hard to design sometimes. Yeah. What time is it actually? Oh, okay. We have actually quite a lot of time. Yeah, I mean, in the session 2, actually, we had on Monday, we didn't actually go over a lot after this part because it was confusing, like first of all. But okay, but I mean, this is sort of like an idea that you want to inject in your mind that as early as possible. Especially you concern yourself with something with like competitive programming or computer science, because DP is extremely important. Like, especially later when you do programming, like algorithms. Also, this problem is really challenging. It's gonna be like I think it's at least LeetCode hard problem. Okay, I want to spend like make a little divergence right now. So we talked about the basically the text justification problem right now. So I want to make a little divergence and talk about what is something called parent pointer. So this is not a problem. This is called a DP technique. This is just a DP technique. So okay. So all of the previous problems we have solved so far, right? So the Fibonacci number problem, right? The shortest path problem, right? The one we covered last time, and the one we covered today, which is the what is it? God, I can't remember. Oh yeah, test justification. Okay, all of these problems we have covered so far, right? It's trying to do some type of optimization. I mean, at least these two, definitely, like shortest path problem and test justification problem. All of these two are trying to make some sort of optimization, right? So the return result it gives you is that it's a value. So for this one, right, it gives you the weight of the shortest path. Like it's like, for example, if you start with a single source node from the S to B, and it gives you output, like basically this thing that it will output you the shortest weight of the path. So it's a number, right? So this path or this part, like using the like the solution we have previously, will give you a number, possibly like say 100 or something like that, right? That's the DP we have covered so far. And for the test justification, will also give you a number, right? It gives you the penalty, like the minimum penalty globally. So it should be like could be 80 something, I don't know. But okay, so the point is that all of the DP techniques we have covered so far, it gives you these kind of numbers, but it doesn't tell you exactly how to obtain this kind of number, right? You only know that this is the global one, but you don't know how did you arrive at this answer. So what parent pointer allows you to do is that it gives you basically gives you a map that how I arrived at this really excellent answer. Like, okay, so that's what parent pointer is. So it gives you leaves you this hint that what's your procedure to specifically arrive at this answer. So specifically, okay, let's say if we use this as an example, shortest path as an example. So from the starting node to the end node, right? So we know that the shortest path could be just like going to this edge first, going to this node first, and then to this node. So we know that like the shortest path is the answer is 100, right? But we want to know that which exact path leads us to this answer. So what parent pointer is that it gives you this path. So it tells you that you should go along this path and give you like the minimum weight, which is just 100, which could be 50-50, right? So it will give you like as U1, sorry, U2 maybe. This is U1, U3. So the output using the parent pointer would just be as U1b. It gives you exactly the way to arrive at that optimal solution. So yeah. Okay, so the way to do parent pointer is similar to DP, but eventually you do something. How many of you learned about the depth first search or the breadth first search? All of you? Okay. So in the depth first search and breadth first search, right? Depth first search and breadth first search. Right? You have basically you're visiting all of the other nodes. And you remember that you store the parent of the current node. So let's say if this is the node 1, this is the P node, this is C1, C2. So you have the parent node, then you remember that you use sort of a map to remember that which node it came from. So in this case, if you check the C1, right, it gave you the P. So this map gives you the parent of this node. So and if you check C2, it also gives you P, because the parent of this 2 is just P. And if you check the P, it gives you none, because P doesn't have a parent. Right? This is what we learned in the depth first search or breadth first search. It gives you parent. So parent pointer is using exactly the same approach, because remember that DP is one of the view of DP is that it's like an acyclic graph. So in the Fibonacci example, right? DP is just add a lot of acyclic graphs, try to solve the subproblems. 7 minus 1, minus 2. Okay, so a lot of DP can be viewed in this kind of type of acyclic graph approach, right? So that's where why the parent pointer makes sense, because essentially you are trying to remember how you arrived at this optimal solution by backtracking where you came from. Right? It could be from this node, and you backtrack again to the next node, and then you remember this path. That's basically the path that leads you to the optimal DP solution. So that's where the parent pointer came, the idea came from. It's actually from the graph theory. So yeah. Okay. So eventually, you also build up this type of table, and you remember, always remember that where leads you to this optimal solution. You always, and then you recall each time, and it gives you the path of the optimal solution. Does this make sense? Makes sense or? Okay. So our parent pointer. That's the parent pointer. Okay. I mean, believe me, yeah, it's gonna be once I give you not really challenging DP problems, but some simple ones. You're gonna see how each of those 5 steps will apply, and that's gonna be way more efficient. I think that's literally a faster way to learn. If I realize the problem first, then you do it, and then you see how this thing can be addressed. Then, I thought it probably would be better, but I mean either way. Okay, but anyway, here I'm just saying that I hope some of this makes sense. But a lot of times, so the reason I'm mentioning this is because in some interview problems you have, right, the interviewer asks you to give him the answer of the DP, which is just a number, what will be the, let's say the knapsack problem, or any any type of optimization problem. He just asks you to what will be the answer for this problem. Then you just want a number, right? But if he asks you what will be how did you arrive that answer? You want to give him which one you take first, and then which path you go first, and which node you go first. That type of thing, right? You have to use the parent pointer technique, which is just literally trivial, right? Because if you already arrived at this answer, it should take you very little amount of effort to find out how you arrived at that answer. Because essentially you just remember how you arrived at it. That's the parent pointer technique. Yeah. So this is 2 different types of DP problems, but I would say this one is trivial. Once you find the optimal solutions, it shouldn't take you very long. It should just be some kind of once you understand how to find the optimal solution, it should just take you very little effort to understand what is a parent pointer. Yeah. Because essentially they're equivalent. Okay. So I guess have surprisingly we have a little more time. Okay, we do have some time, 15 minutes. Okay. All right. Let me think about it. Okay. So we can go over blackjack, which is another DP problem, or we can do something like a little bit simpler. What's your preference?
Blackjack.
Blackjack? Okay, sure. Yeah. Okay. But blackjack is harder though. Okay, whatever. Okay, we can go to blackjack now.
Is there enough time to do that?
Yeah, we have
15 minutes.
we have time to at least say some of it. It won't take very long because we won't go over like exact algorithm. We're just gonna go over like the DP idea behind it. So yeah, it shouldn't take too long. So okay, so blackjack. Okay. Any of you played blackjack before? Or played blackjack? Actually, this is all of the topic, but actually Rice has a weekly blackjack. I don't know. I don't think blackjack. It's probably Texas Hold'em, and it's like at Dunkin' every week. So it's pretty interesting. Like, you can check it out. Or if you want to, I can send you the person who hold it. So in case you're just interested. Okay, but I'm just gonna go over briefly what is the rule for blackjack. So blackjack is just some game you play, and so basically you have a dealer, you have a lot of players, could be multiple players, and but in this today we're just gonna cover one player. So one player versus one dealer. That's all we're gonna do today. So in blackjack, okay, I was about to bring a deck of cards, but okay, I didn't actually have one, so whatever. So okay, I'm just gonna go over the rules for it. So suppose that I'm the dealer, and you are the person who I'm playing with, right? You are the player. Which my purpose is just gonna win you all of your money, and your purpose is the vice versa. Okay, so the rule is that we have a deck of card, right? So I'm gonna give you 2 cards first. I'm gonna give myself. I'm the dealer, right? I'm gonna give myself 2 cards first, and then I'm gonna give you 2 cards, and then you're gonna see if you want to hold it. You want to stand, or you want to basically want me to give you another card. I think that's the way to say it, but. Maybe not exactly right, but okay, if you have more than 21 points, you lose, essentially. But if you have less than 21 points, which is from 1 to all the way to 20, the closer you are to 21, basically, okay, so which one of us is closer, that determines which one of us. Okay, so if I have 20 points, and you have 21 points, right, so you would win, right, because you are exactly 21. But let's say if I have 20 and you have 22, then I will win, right? Because you actually exceed the all of the you actually exceed the 21. So that's also this is not good. This is good. Another rule is that you have A, right? A is just actually it can be either 1 or it could be 10. So this is another interesting rule here. But it's actually ridiculously simple. So just literally okay, so initially, I'm going to have 2 cards. Give myself 2 cards. And I'm going to give you 2 cards. And you can choose either to stand, or you can either ask for another card. So, okay, so the thing is that if you ask for another card, right, so you have a higher chance, sort of a higher chance, to get closer to 21, right? But at the same time, you have a risk to exceed 21, in which case you just lose the game. But so you can either choose to stand. In which case, I believe if there's a math paper on this, if you are 17 or above, you should choose to stand. You shouldn't ask for another card. But if you're less than this number, you should ask for a card. Not very accurate. I'm not an expert on this thing, but yeah, but just something like that. Okay, but dealer can't ask for another card. I don't think a dealer can ask for another card. So the dealer's play is just gonna be very deterministic, right? Dealer always has 2 cards, which is kind of supposed. Dealer always gonna have 2 cards. So you can ask for either have 3 cards, or even more, as long as you want to hit always. So you can choose to hit or stand. So if you hit, I'm gonna give you another card. If you stand, that's it, all the card you have. It makes sense? The rules. Yeah, but if you hit, and then if the number of cards, like the points you got, if the sum of them like exists 21, you just lose immediately. So you can't hit again if you already like have a points over 21. This makes sense? Okay. Looks like none of you play very long, like this poker games. Okay, but today we're gonna cover blackjack right now with dynamic programming. But it's not actually something you can use very much in the in Vegas because we're gonna deal with a very specific type of blackjack. It's called perfect information blackjack, which is saying that suppose you know all of the cards in the deck beforehand. So kind of not very practical, but okay, good for example. So just to say you have a deck, right, and you know all of the card within this deck because you have a person like with in the Vegas with you. No, I don't know. Okay. So you have a deck of cards, right? So what will be the last card? Wait, there are 52 cards or 54, right? 51. Sorry. Alright, there are 52 cards, so it's just gonna be a deck from 0 to 51. Right. Okay, I'm not good at memorizing this. Okay, so this is a deck you have, and then second thing is that it's one player versus dealer. Right, okay. And another thing is that, let's just suppose it's gonna be $1,000 bet per hand. Okay, so this is all of the rules we have. Can you tell me why? Okay, this is something always like very interesting to reason. Like why you think greedy algorithm won't work in this case? Okay, whenever you see a problem that's about optimization, always think about greedy algorithm first because that's way faster. But if it can't work, then maybe just aim for dynamic programming. And if dynamic programming will work, probably either you didn't have it or it could be just brute force. But brute force is very rare. Most time, if it really doesn't work, then just dynamic programming. So why do you think like dynamic programming won't work in this case? Like if our objective is to win as much money as possible. Any idea? Like using the same analogies before, like the way we think about task justification. Any idea? Jane, do you have any idea?
Why greedy doesn't work or why dynamic programming doesn't work?
No, greedy, right? Why greedy doesn't work? Dynamic programming is the topic we're going to cover today, so it has to.
I'm not sure.
Okay. Yeah, okay, I'll just go over. So the reason why greedy doesn't work is that, again, the same reason, you want to achieve global optimization instead of a local optimization. So for example, let me give you a very clever example. So there are cases actually you want to lose this round. Does it make sense? So if you use dynamic programming, your goal is to want to achieve global optimization, not local optimization. So it's not like, okay, let's see why we want to do it. So you have a deck of cards, you know all the cards already, right? So in some scenarios, you know that the next round you're gonna lose. Like you know that the next round you will win more if you lose this round. Does it make sense? So you opted to give up in this round. So because okay, let's say you have an ace in the next round. Okay, so let's say if you lose right now, so the dealer won't deal you another card. The next round you can have an ace. But if you don't lose, next round you can have something really bad. So you want to sort of lose this round temporarily and then win it back next round, even win more, right? But greedy is always so the bad thing about greedy is that it's always trying to think to win this round, always. So even if you can win this round, sometimes you shouldn't use dynamic programming idea because you want to achieve global optimization, not local optimization. Does it make sense? Greedy can achieve local optimization. A greedy can win this round as much as possible, but next round, not really. Right? But in some scenarios, greedy can really do it well. And as long as you can prove that your greedy always works. But this case is doesn't work. It can give you plenty of contradictions, examples. Yeah. So that's why greedy won't work. Okay, I'm just gonna go briefly over like how do you solve this problem using dynamic programming. It's really, really similar to text classification. So once you see that, like we're gonna see two types of problems. One is this one. Sorry, one is the suffix problem. This is also the suffix problem. So we're gonna see two types of problems. One is called suffix, the other one is prefix. And the third type of dynamic programming problems involves two dimensions. So it's gonna be ij this time really. But the prefix is just the suffix is just gonna be I comma, right? It's I comma using that Python notation. And prefix is just gonna be comma I. Like this, you try to find all of the previous values. Suffix you try to find all of like the next values. And the third case is just gonna be ij, so which is you want to find the values within these two bounds. But these are just little like most of the dynamic programming problems are gonna be covered by three of those. So this problem is the same as the test justification that you also use the suffix, the idea to think about suffix. So each time you play the card, right, you can choose to hit or not. So what is the difference between hit and not hit? So if you hit, right, basically you use this card, right, you use all of these cards if you hit. So if you use it, then you leave it, then you have some cards left, which ends with 51, which is last card. So this is exactly the suffix, you can see it. This is suffix, like exactly as the test justification. So you have like a subproblem that ends with the end, right? But you always play with the at the beginning. So in this case, we don't suppose it shuffles, right? Because shuffles is not good. Yeah. So we suppose that it doesn't shuffle. The card is never shuffled. And then if you play from the top, you always get this card first. And then the problem you're left with is just this subproblem, which is the suffix. Yeah, so this is also that's a way to think of it as this is also a suffix problem. So the guessing is actually really simple. The guessing is just going to be how many hits you're going to do, right? Okay, so literally you can hit as many as n times, where n is just 51. So you can, 52. You can hit all of the cards, right? You use up the whole deck, but it's guaranteed that you're going to lose because you already exist 21, right? But so in this case, it's just but the only part you're guessing is that how many times you're gonna hit. So if you hit some cards, right, the first one, this, and you choose to hit two times, then the dealer gonna have the first two cards. This is two cards from dealer, and then you have two cards yourself, and then you hit two times. So you're gonna have four cards, which is the two cards after that. So all you are guessing is just how many times you're trying to hit, and that's gonna give you a deterministic result, like how many points you have. Based on that, you can try to compute whether you lose or whether you win. If you win, then you basically just go to another state. So dynamic programming we covered this, right? It's called state. So you can, depending on the number of hits you can hit 2 times or you can hit 0 times. So you go to another state. This state basically is saying that you have this number of cards left and this is the amount of money you have currently. So you always remember those two things, and then you try to optimize the amount of money until you eventually run out of all the cards, which in which case suffix is 0. That's the base case. So yeah, this is okay. So the way to write a dynamic programming, the formula is exactly the same as test justification. So I mean, literally it's exactly the same because it's the same suffix type of problem. So it's the same as suffix. So BJI, remember that what we wrote down the test justification is exactly the same. But in this case, you want to do the max instead of the minimum because that's a penalty function. In this case, you want to maximize the profits, so you do the max instead. So the max of BJI is just the max of the outcome you have in this problem. So outcome of this round literally just if it's either you win $1,000 or you lose or you tie, right? It could be tied because you have the same points as the dealer, or it could be negative 1,000. So you win 1,000, you tie, or you lose negative 1,000. Plus the suffix, which is plus the suffix, which is the subproblem, which is j, right? Where j is just all of the cards after the where j is just from I plus 1 to let's see, I plus 1 to 52. Right. This is j is just after it has the cards you start over. So this is you see Okay, so this is exactly, if you compare it with the test justification, you're gonna see that the only thing we changed is this part, max, right? Because this is just not a penalty function, this is like a profit function. So you want to maximize this part. That's all it changes, but everything else remains the same because it's the same type of suffix problem. So hopefully it makes some sense. Yeah. Does it make a little sense or yeah? Try to solve little problems. You're gonna get more confused. And then like so I mean after that it's gonna get kind of like easier. Yeah. And also I think that so most of the time when I do dynamic programming problems, like I would say 4 out of 10 times I can't really solve it because it's just really hard. But it takes like it's not really something that's mechanical. It takes some little like this is all the part that's really hard, right? But once you figure this part out, like once you see how it can be solved, you use dynamic programming. That's it. The whole game wins basically. But yeah, that's basically it for this time. So hope you have a nice weekend. Thank you. Okay, see you next week.